Welcome to chapter 4. Today, in this video, we are going to look at the concept of probability. We will look at an introduction to probability. This is a topic where I say we are transitioning from descriptive statistics to inferential statistics. We are midway in our journey. All right. This probability is an interesting topic which helps us to understand uncertainty. In this video, we are going to look at how to identify situations for which each of the three approaches to assessing probabilities applies. Now, we're going to look at how to apply the addition rule, how to apply the multiplication rule, and finally, you would, at the end of this video, know how the Bayes theorem for applications involving conditional probabilities are utilized. So that's what we are going to explore in this video. And of course, in everything, there's so much new vocabularies that we're going to learn in this video. Now, if something has a low probability, what does that mean? If something has a low probability, it means that it's rare, it's unusual, it's unlikely to happen. If something has a high probability, it means that it is usual, it is likely to happen. All right. We looked at that when we looked at the empirical rule, remember? And we talked about the z-score and how it relates to probability. And that's what you're also going to learn in this chapter and the next. Okay, so let's talk about probability. What is probability? How would you define probability? Think about it. You can define a probability as the chance that a particular event will occur. Okay. You can also define a probability. So probability ranges between 0 and 1. So those are the ranges of probability. So you can have a probability that is close to 0, a probability that is close to 1. Some other terms that we might use in this video is the concept of an experiment. I know we've seen the word experiment in chapter 1. Now, when we say an experiment, we're going to look at it as a process that produces a single outcome whose results cannot be predicted with certainty. So that's what we will refer to as an experiment. And I would also use the term sample space. As well. So a sample space is the collection of all outcomes that can result from a selection, decision, or experiment. So let me put some vocabularies and definitions. So you would hear me use the word event. What's an event? An event is a collection of outcomes. Of a procedure. Okay. Now, we also use the word a single event. And of course, in your textbook, there are other terminologies that are used that I might not really use in this paper, in this video. Now, if you have any question, please reach out to me. A single event is basically a single outcome. And then I mentioned the sample space. What's a sample space? Who remembers what I just said? I said the collection of all outcomes. So a sample space is all simple events. All simple events. So every possible outcome, that's the sample space. Okay, so let's move on. So here, let's put things in context with some examples, make it easy to understand. Now, if I say that the probability of an event succeeding, so the probability of a new business to succeed is equals to 0.25. So we're saying that the chance of a new business succeeding is equals to 0.25. So what's the chance of the business not succeeding? So that would be basically 1 minus 0.25. Okay, so that's an example of a probability, the chance of the event succeeding. Now, I could also ask you, when I said an experiment, so the experiment here would be the activities associated with starting a new business. So the activities associated with starting a new business will be the experiment. Now, what is the sample space? I'm going to use SS for sample space. Let me not use SS because it means something else. So the sample space is what? Yeah. So the sample space is basically that the business succeeds or the business fails to succeed. So business succeeds or the business fails. So that's the sample space. So we know the probability of the business succeeding is 0.25. Now the probability that the business fails will be what? 0.75. Okay, let's look at another example. Let's say the chance of a new hire quitting within the first month on the job is, so the probability that a new hire quits within the first month of a job is equals to 0.10. What is the experiment here? So the experiment here is employee is hired and begins work. That's the experiment. What's the sample size? The sample space? Employee quits or employee does not quit. So it's binary. Employee quits or employee does not quit. I hope you're following the whole concept. Let's look at a different example. Let's say now I have a procedure in which I flip. So what I also use the word procedure. Procedure is basically what you are doing. So let's say I have a coin. I usually have a coin and cards. Not here today. Okay. So I have a coin, and your coin could be heads or tail. Now, if I flip the coin one time, I can either have a head or I have a tail. So let's say in a procedure, I flip the coin one time. And let's say I'm looking at the event of having a head. What's my sample space? Think about it. What's the sample space before I write it? Exactly. So the sample space in this case is simply head or tail. So I flip the coin one time, and the possible outcomes are head or tail. It's either I have a head or I have a tail. Okay? What if I flip the coin 2 times? What will be the sample space? So if I flip the coin 2 times, or let's just go 3 times, so, or I'll just give you a general formula. If you flip the coin, if you flip k time, then the sample space will be 2 to the power of k. So when we flipped 1 time, 2 to the power of 1 is 2. So our sample space, the size of our sample space is 2. If we flip 2 times, then our sample space, so if we flip your coin 2 times, the sample space, the size of the sample space will be 2 to the power 2, which is 4. How do we get that? So when you flip 2 times, so in the first time you can either get a tail and a tail, or you can get a tail and a head, or you can get a head and a tail, or you can get a head and a head. So this is 1, 2, 3, 4. So that's the sample space. Okay. Now, if you flip 3 times, flip the coin 3 times, the sample space will be 2 to the power of 3, which is 8. And how do we get that? I'll show you. It's a simple trick. So the first time it's going to be T, T, T. So tail, tail, tail. Now, since it's 8, we're going to divide 8 by 4. So in the first case here, we're going to have 4 truths, T, T, T. And then next, we're going to have 4 of them, H, 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 H. Now, in the second row here, we're going to divide this 4 by 2. So this is going to be TT, HH, TT, HH. And then the next, we're going to divide this by 2. That's 1. So it's going to be TH, 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 TH. And voila, we've actually written everything in order. Each of these outcomes are unique. And this is a way of counting also in binary. Because when you're counting in binary, so this is going to be 0, 0, 0, which is 1 in decimal. So you have 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 0, 1. This is actually in ascending order because the decimal equivalent it will be 0, 1, 2, 3, 4, 5, 6, 7. For those who knows how to convert binary numbers to decimal, which is not part of this course, would understand what I've just done. And that's how we came up with this sample space. Very easy without thinking. So if you count a number of single outcomes, you have 8. You have 8 total single outcomes. All right. Now, given the sample space, if I ask that, what is the probability of having 1 head and 2 tails? So meaning that the event is 1 head and 2 tails. So how many ways can we first, before we get probability, how many ways can we have for 1 head and 2 tails? So look at this. 1 head and 2 tails. This is 1. 1 head and 2 tails. This is 2. 1 head and 2 tails. So let's look again. 1 head. No, I mean, we start again. 1 head and 2 tails, not 2 heads and 1 tail. Okay, let's go. 1 head and 2 tails, that's 1. 1 head and 2 tails, that's 2. 1 head and 2 tails, that's 3. And that's about it. So there are 3 ways So the answer is 3 ways. Okay. Now, if you also look at the probability, it's going to be the total number of events divided by the total sample space. We'll get there. So that will be 3/8. But like I rephrased the question to asking, how many ways can we have one head and two tails? How many ways can we have 3 heads? Obviously, it's only one way, but we can have 3 heads. How many ways can we have 3 tails? Obviously, only one way as well. So now that you understand that we can use these words to define probability. So what's a probability? We said earlier that is a chance. How do we put it? So the chance that a particular event will occur. Okay. So we can also define probability as the likelihood of an event occurring. So apart from chance, I like using the word likelihood as well. So probability is the likelihood of an event occurring. Okay. So if I have an event, so usually for probability, we use the Greek letter P. I mean the English letter P. And then for events, we generally use the capital letters. Like we can have an event A, you have an event B, and so on and so forth. So we use capital letters. So if I say the probability of event A, this means that the probability of event A actually occurring, that's how you would express this. So P of A means the probability of event A actually occurring. So if this was my event here, the event size is 3. So the probability, if this was A, so the probability of A will be equals to the number of ways, which is 3, divided by the sample size, which is 8. That will give us the probability of A. But I'm jumping the gun. Let's talk about probability. There are generally 3 types of probability. And the first one is called observed probability. So this is a probability that is estimated based on your observation. So take, for example, I have a coin and I'm flipping the coin 1, 2, 3, and say I flip the coin 100 times. And out of 100 times, I recorded the number of times I had a head while flipping. And so let's say I had 30 heads after 100 trials. So the question now would be, what's the probability of having a tail if I ask? So that would be simply, if I had 30 heads, it means I had 70 tails. So the probability of having a tail will be what? You can already guess what that means. That will be 70 divided by 100. Okay, so that will be the probability. So that's an observed probability. So an observed probability, so let's say the probability of A will be equals to the number of times A occurred divided by the number of trials, or the number of times the procedure was repeated. Okay, so that's how you determine the observed probability. Okay. So this tells us what happened, what did happen. So you're doing something and it tells us what did happen. Now, the second type of probability is known as the classical probability. And this is generally based off on theory. So the classical probability is based on the chance of an event occurring. Um, and so it's based on the chance of an event occurring. Yeah, you're not observing a procedure occurring. So this is based on theory. So the probability of an event A is simply the number of ways A could occur divided by the number of simple events or the sample size or the number of outcomes. And that's what I did right here to compute this. So 3 is the number of ways A could occur, and 8 is the number of simple events or the sample size. So this is known as the classical probability, which basically computes what should happen. So that's what should happen. All right. And the third type of probability is the subjective probability. What is subjective probability, by the way? Think of the word subjective. When we say something is subjective, what do we mean? So a subjective probability can be defined as an educated guess. An educated guess. So take, for example, you have a problem and you decide to go to see the doctor. And you decide to see 3 doctors on a particular day. Now, one doctor tells you the probability of you having this problem is 90%. You meet another doctor and they say, they conduct their test and say the probability of you having this problem based on the information you give them is 85%. Then you go to another different doctor and they say the probability is 96%. Now, as you can see, these values are not consistent. They're not the same. So it's just based on an educated guess. So that's a subjective probability. It's more based on the personal knowledge of the individual, you know. So subjective. All right. Sounds good. Now, with all of this, you are all set. You all now have a clear understanding of what probability is. You know what an experiment is. You know what a sample space is. So those are key terms to take into consideration, what the sample size and so on and so forth. So that's the basic concept of probability. Now, let's look at how to compute some probability. Let's have our cards ready. All right, I think I'm going to do this without shuffling a card. So assume I have my cards and I shuffle my cards. Okay. And I asked you, so the probability of selecting a heart from a deck of cards. So what's the probability of selecting a heart from a deck of cards. So first, what's the event? It's the hearts. How many hearts are there in a deck of cards? So there are 13 hearts. How many cards are there in a deck of cards? There are 52 cards. So the probability will be, if you compute that, 0.25. Now, is this a classical probability? Is this an observed probability? Or is this a subjective probability? What type of probability is this? Clearly, you didn't observe me conducting any experiment, or you didn't observe me doing anything. So this is based on what should happen. So this is classical. There was no procedure that I conducted. So we say this is classical. Classical probability. All right. Now, I earlier just gave an example and I said, let's say I flip a coin 100 times. So I flip coin 100 times. And let's say, well, let's say you flip the coin 100 times and you get 45 tails. Now, my question for you is, what's the probability of a tail? That simply equals to 45 divided by 100, and that is 0.45. So we can say that you have 45% chance of getting a tail. Now, is this observed or classical? It is observed because you observed me flipping the coin 100 times. So it's an observed probability. Okay. Let's see. Let's look at a different example here. Or let's tie into the whole rules of probability. Let's proceed faster. So rules of probability. So one of the first rule, as we said, is that the probability must always be between 0 and 1. So the probability of an event A is less than or equals to 1 or greater than or equals to 0. So you can have a negative probability and you can have a probability more than 1. So if you compute your probability and you're having a value more than 1, then it means that you're doing something wrong. And thereby you need to stop and verify. Okay. When I talked about events, when you read your textbook will tell you about 3 types of events. You have mutually exclusive events, you have independent events, and you have dependent events. Read through the textbook and I would explain what this term means as we move along. But just for you to take note of them so that when I use it, you try to connect the meaning. What is the other rule? If the probability of an event A is equals to 0, what does that mean? It means that it's an impossible event. What about if the probability of an event A is equals to 1? It means that it's a certain event. It's definitely going to happen. So yeah, A is taken as any type of event. Now, there's also one concept known as the law of large numbers. So let's say I'm flipping a coin and I'm recording the number of heads and tails. And I flip this coin 1,000 times, 1,000,000 times, or I create a simulation that does this flipping. You would notice that the probability of the head and the probability of the tail would tend towards 0.5. This is known as the laws of large number. So which means that the more a procedure is repeated, the closer the observed probability will get to the classical probability. So in terms of the law of large numbers, the observed probability tends towards the classical probability. So what I said is that the more a procedure is repeated, the closer the observed probability will get to the classical probability. Okay. All right. So let's look at a different term known as a complementary event. So a complementary event is, for example, success, failure, kind of complementary. Okay, so events which are mutually exclusive. So which means that they can't happen at the same time. So those are complementary events. So we say, so mutually exclusive events. So these events can happen at the same time. So for example, let's say I have an event A and I have the complement of A. So take, for example, I create a Venn diagram here, and this is an event A. The unshaded area outside the circle, so this is A, this will be A complement, which is the area that is not shaded. So what we said is that these are events which are mutually exclusive. So these events can't happen at the same time. So two events are mutually exclusive if the occurrence of one event precludes the occurrence of the other event. So these are mutually exclusive events. All right. So let's look at other examples. So another example could be rolling a. So let's say the event here is rolling a 5. What's the complement? The complement is not rolling a 5. So the complement will be the set of either I had 1, 2, 3, 4, or 6. So that's a complement. Now, if I asked you, what's the probability of rolling a 5? Of course, you know that that will be 1/6. This is classical probability. So the event size is just 1. The sample space is 6. What's the probability of not rolling a 5? Again, here, what's the event size? 1, 2, 3, 4, 5. So there are 5 numbers in that set, in that event. What's the sample space? 6. So the probability of not rolling a 5 is 5/6. And of course, if you add the probability of a 5 plus the probability of 5 complements, that should give us 1. 1 over 6 plus 5 over 6 is equals to 1. So by complementary rule, we are saying that the probability of A plus the probability of A complement is equals to 1. So which means that the probability of A complement is equals to 1 minus the probability of A. So this is the known as the complementary rule. Okay, so let's move on. So next we're going to look at the addition rule for probability. So by the word addition, it means that we are saying that there are more than one event we'll be looking at, okay? So what we are really saying here is that we have a compound event. So a compound event is an event that joins 2 or more simple events. Think of it as a compound sentence that joins 2 or more simple sentences. So that's the idea. So it's an event that which joins 2 or more simple events is a compound event. So let's look at an example. So let's say the probability of rolling a 1 or a 5. So we have a connecting term here, or. So either we roll in a 1 or a 5. So this is a compound event. So it's either, so or is like you either rolled 1 or the other or both. So that's how we can interpret it. So we are saying that what's the probability? Let's say the probability of rolling a 1 is one event. The probability of rolling a 5 is another event, say B. So we can say the probability of A or B. So which means the probability of A occurring or B occurring or both A and B occurring in a single trial. Okay. Now think about this. So I have A and B, and I want to have A or B. When is A or B true? Let's look at the truth table. 0, 0, 1, 1, 0, 1, 0, 1. Now, when we have an or statement, it is true when either one is true or both. And so that's why we said that the probability of A or B is the probability of A occurring, which will be this, or B occurring, which will be this, or both A and B occurring, which will be this, in a single trial. In a single trial. So that's the definition of the of this probability of A or B. Now we may look at an example to really understand this concept better. Now, or we may look at this from the lenses of a Venn diagram. So let me draw a Venn diagram. And I have this event A and event B. So this is A, B. Now the question is, what's the probability of A or B? A or B can be seen as the union of A and B. the union. So we can put this as A union B in set concepts. So what's the union? So we're trying to, we want to add all of them together. What's the union? So if you see this here, we're going to add, if we add A plus B, what we've done here is that we've added this intercept 2 times. So we need to subtract it. So A or B will be equals to the probability of A plus the probability of B minus the probability of A and B. So A and B is this intercept. So the intercept is A and B. So we have to subtract one of them. And so that gives us the addition of all these events. So probability of A or B is the union of A and B. And that is equal to the probability of A plus the probability of B minus the probability of A and B, or the intercepts. So with these known, so we can try this problem. So let's say we want to find the probability of randomly selecting heart or spade from a standard deck of cards. Okay, again, so this will be the probability of a heart. Let me draw the heart, looks good, or a spade. And so this is going to be equal to the probability of a heart plus the probability of a spade minus the probability of a heart and spade in a single trial, which is impossible. Okay, so clearly this is impossible. So this will be 0. You know, that's an impossible probability to have a heart and a spade in a single trial. It's impossible. So basically, this probability is a sum of these 2 probabilities. And we have seen the first one already, which we said is 13 over 52. Now, what's the probability of a spade? That's also 13 over 52. Minus 0, which is equals to 26 divided by 52, which is 0.5. Sweet. So we have seen here the addition rule. Now my question is this classical or is this observed? Which is it? You clearly didn't see me performing any, you didn't observe me performing anything, any procedure. So this is clearly classical. Okay, so that's really the addition rule. And of course, there are different examples that we can look in the same context, but you just need to remember this rule. So this is the addition rule. Now, let's look at complementary events in terms of the addition rule. So what we are saying here is that what's the probability of A or A complements? Again, this will be equals to, using the addition rule, we know that is equals to the probability of A plus the probability of A complement minus the probability of A and A complement occurring in a single trial. Now we know that the total probability should be equals to what? 1. Should be equals to 1. Because we are saying the probability of A or A complements. Now, clearly, this is impossible. So this is 0. So we have here that the probability of A plus the probability of A complement is equals to 1. And we can see that the probability of A is equals to 1 minus the probability of A complement. The probability of A complement is equals to 1 minus the probability of A. So this is the complementary rule. And you can also apply this to various examples in the textbook as well. And again, you can apply this to the examples on the homework assignments. Now, if I was to give an example here, and I say that the probability of a business succeeding, so the probability that a business would succeed, if I say it is 0.512, for example, now what's the probability that this business will fail? That will be equal to what? That will be equals to 1 minus the probability that the business succeeded. Okay. And that will be 1 minus 0.512. If you get off your calculator and do the computation, you should have 0.488. Okay. So that's the addition rule. Next, let's look at the multiplication rule. And so we're looking at the multiplication rule for AND probabilities. In the other case, we talk about things happening in a single trial. But in this case, the AND will be probability of A occurring and then A complement occurring, not in a single trial. That's really the main difference between the multiplication rule and the addition rule. Meaning that if I say, what's the probability of A and B? Previously, we'll say that in a single trial, the probability of A and B occurring in a single trial is impossible. But in this case here, we're saying what's the probability of A occurring and then B occurring? So this and can be written as and then. Think of it as and then. So in successive trials is what we're saying. So what's the probability of A happening and then the probability of B happening in successive trials? Yeah. So let's look at an example here. And so let's say I'm conducting a test with only 2 questions. And so for the first question, it's a true and false question. And I'm asking, does Dr. Italma play musical instruments? True or false? So it can either be true or false. So for those who know me, will know what the answer is. The second question, multiple choice. My favorite color is what? I'm sure it's very obvious. For most of you who have watched all my videos so far, you would see a color that is consistent. But well, these are the options. A, red. B, blue. C, green. D, black. And E, yellow. It can only be one of them. Now, what's the probability for the first question? If I say, what's the probability does Dr. Itauma play a musical instrument? So it's 50-50. So what's the probability that is right? That will be 1/2. For the second question, what's the probability that any of them is correct? That will be 1/5. So this will be 1/2, and this will be 1/5. That's what should happen, and that's known as a classical probability here. Now, if you guess randomly, what is the probability of getting both questions correct? What's the probability of getting both questions correct? You know that both questions are independent of each other. What's the probability of getting both questions correct? So we're going to create a tree, a tree. So for the first level, it can either be true or false. And then if it's true, it can either be A, B, C, D, and E. And if it's false, next it can either be A, B, C, D, and E. And so with these, we can create the sample space. What would the sample space look like? So the sample space is the set of, we could either have true and A, that's one single event, or true and B, true and C, true and D, true and E, and the same for the next one, false and A, false and B, false and C, false and D, and false and E. So one of these is correct. So looking at this from classical probability, what's the probability that both are right? So what's the probability that both is right? From classical probability, now that we know the sample space is what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that will be simply 1/10. So the event here is 1, not this event size. So that which is correct, the event of both being correct, is just one of these tuples. And the sample size is 10. So the probability that both is right is 1/10. So this is what we've known before. And of course, the examples that I might give you might be in such a way that it would be hard for you to create the whole sample space. This is pretty small, so it's easy for us to visualize this and write it out. What if we have a very large sample space? That's where the multiplication rules comes in handy. And that's what I'll be showing you. So I'm going to show you how to derive this answer using the multiplication rules as well. Now, to get into there, let's look at the concept of conditional probability. So a conditional probability is of an event occurring. So the probability that an event occurs given that another event has already occurred. So what is that? What are we saying? So if we see something like this, the probability of B, and then there's a pipe A, this means that what's the probability of B occurring given that A has already occurred? That's how to interpret this. So this is a conditional probability. What's the probability that it's going to be sunny given that it had already rained, for example? So those are the conditional probability. So we want to compute that probability, and if it's small, then there's a lower chance that it's going to be sunny. If it's large, then there's a high chance that it's going to be sunny. Okay. So the probability of event B occurring given that A had already occurred. All right. So before we go into this more, let's look at the other concept called an independent event. We've looked at a mutually exclusive event. What of an independent event? So an independent event means that the occurrence of one event does not influence the occurrence of the other events. So the occurrence of one event does not affect the occurrence of the other events. So the fact that A occurred does not affect B, does not influence the condition on B. So what that means is that if A and B are independent, if A and B are independent, so it means that the probability of B given A is simply equals to the probability of B. So B is not influenced by the fact that A had already occurred. Okay, so B is not influenced by A. So A and B are independent. An example would be when you roll a die. So what's the probability, say, that 2 occurred given that 3 had already occurred? That simply equals to the probability of 2. Okay? So does rolling a 3 affect the probability of rolling a 2? Simply no, it doesn't affect it. So this is considered independent. So rolling a 2 and rolling a 3 are two independent events. Okay. And so these are key concepts to take into consideration. Now let's look at another example, drawing cards. And of course, you can apply this to different business contexts. So let's say, what's the probability of drawing a queen, given that we have drawn a 9 with replacements? What is it? So when we say with replacement, so we've drawn a 9, we took a 9 out, and then we put it back in the deck. So it simply means that this is equals to the probability of Q. So these events are independent. And that will be equals to what? How many queens are there? There are 4 divided by how many, what the sample size, that's 52. So it's about 1/13. Okay. What about if I say without replacements? So what would be the probability of drawing the Q given that 9 had occurred without replacements? So I draw a 9 and I keep it on the table, and then I want to draw a queen. What's the probability of drawing a queen, given that I'd already drawn a 9 without replacement. So that's a different situation. So now the sample space for number of queen is still what? Is still 4. But the sample space, because I kept 9 on the table, I now have my deck, the sample space is now reduced by 1. It's no more 52, but it's now 51. So that will be 4 divided by 51. Now, the question here is Q and 9 independent? Of course, it's not independent. It's dependent this time. So Q is affected by the fact that 9 had already occurred. So this is considered dependent. We need some dependence. Oh, sorry, we need some independence. Does not relate. What about the probability of drawing a Q, given that you had drawn a Q with replacements? So I drew a Q and I put it back in the deck of cards and I drew another Q. So this is simply equals to the probability of drawing a Q. So this is independent, which would be same thing as saying 4 over 52, which is 1 over 13. So this is independent. Now, what if I said you drew a Q, even that you've drawn a Q without replacements? Now that's different. So I drew a Q and I did not replace it. So how many Qs do I have? I would have just 3. So because I have 1 left on the table, so I'm left with 3 in the deck of cards. So this will be 3 over 51. Okay, you can see how interesting probability can really be. Okay, so that's the whole concept here. And so with this, there's something that we could see that is happening here. The probability, so right now we're really ready for the whole multiplication rule. The probability of A occurring and then B occurring is simply equals to the probability that A had occurred times the probability that B has occurred given that A has occurred. Now, if A and B are independent, it would mean, so if A and B are independent, then it means that the probability of B given A is what? Is equals to the probability of B. And what does that mean? That would mean that the probability of A and B, that is the probability of A occurring and then B occurring, is equals to the probability of A times the probability of B. See that? Sweet. So if A and B are independent. Now, if we go back to our previous example, and I'm sure you guys are having fun, right? Cool. So these two events are independent events. Solving the first question and the second question are 2 independent events. So one does not affect the other. So the probability that both are right is simply equals to the probability that of I times the probability of II. So I being the true and false, which is 1 over 2. And the probability of the second event is 1 over 5. And if you multiply both of them, you have 1 over 10. And that's what we got here. So that's the multiplication rule. Pretty easy. So now you have learned about the addition rules, and you've also learned about the multiplication rule. And at this point, I would end this video, and in the second video, we will complete the whole concept of probability.